Welcome to Units of Measurement. Alright, so when we measure things in science, what we mean by measurement is a quantitative observation. Quantitative meaning quantity. We're measuring some quantity, not quality. So a measurement always has two parts. It's got a number and it's got a scale, a unit to it. So if we say something like 6 feet, I'm 6 feet tall. I could also measure that in different units, like 1.83 meters. If all I say is I'm 6, it doesn't mean anything. We don't know what I'm referring to. Am I 6 years old, 6 days old? Am I 6 feet tall, 6 miles tall? Am I 6 minutes away from home? We need to have both the number and the unit. We need to know what scale we're referring to. So we could also have something like, for volume, 2.0 liters, which is the same as roughly 2.11 quarts. We could have 1 hour, 60 minutes, 5 moles of carbon atoms, or 3.01 times 10 to the 24 carbon atoms. Note here that it's not enough to say 5 moles, because we're not specifying 5 moles of what, right? We need to say 5 moles of carbon atoms, or we may abbreviate that something like 5 moles of carbon. What we mean there is the same as 5 moles of carbon atoms. Without putting that moles of carbon or of aluminum or whatever, we're basically not saying the entire unit. Something like feet is enough. We know what we mean when we say a foot. Right? So if I say 6 feet, you know that it's 6 feet long. Whatever it is that I'm measuring is 6 feet long. But if all I say is 5 moles, you don't know what it's of. 5 moles of feet? 5 moles of rabbits? We need to specify what it is. So when you write moles, you should always write something afterwards. A substance, usually. An element, a compound. If you're measuring something like rabbits, we don't have a mole's worth of rabbits on Earth, but if we did, you would want to specify rabbits there. So something like 2 dozen donuts is the same as 24 donuts. Note here that dozen is now our unit, or rather dozen donuts is a unit that we're using. And in this case, donuts is sort of the unit that we're using. Right? We're counting numbers of donuts. In this case, dozen is a unit. So, when you have a measurement, you always need to write down the units with your measurement. So the Mars Surveyor in 1998, there were 2 parts to the spacecraft. We sent it to Mars, and the orbiter, so this was supposed to get to Mars and orbit around the planet, sending back data and signals from both its own instruments and data signals from the lander that was supposed to land on the surface of Mars. The orbiter was lost, and this occurred because there were 2 different teams, well, a number of different teams working on the orbiter, but one team working on the orbiter supplied some numbers, some quantities in English units, and another team interpreted these as being in metric units, in newtons. And so what ended up happening is that the orbiter got too low in the atmosphere, and that either caused it to bounce off the atmosphere or to burn up and basically crash into Mars. So that of course costs NASA millions and millions of dollars. So always be very, very careful and write down your units so that whoever it is that's using that number, even if it's yourself later on, knows what that unit is. All right. So we've talked about measurements, which are quantitative observations. Now we want to talk a little bit about qualitative observations. So a qualitative observation is an observation of some quality, not a quantity. Right? So maybe my shirt is blue, or it has stripes. So this is something that doesn't involve numbers. If we want to count how many stripes my shirt has, that would be a quantitative observation. But if we just want to say it has stripes, that's a qualitative observation. So another example may be the bunny is soft, or maybe the bunny is dead, or maybe the bunny is undead and it's eating our brains. These are all qualitative observations. But when we move back to quantitative observations, when we have units, in science, we've come up with a standardized set of units. So back in the day, something like a foot in the imperial system, a foot was literally measured using one's own foot. But that meant that my foot is different size than your foot probably, and so if each of us were to mark off some distance, we would get different measures of how many feet there were. And eventually now, of course, the foot is standardized, but we've also come up with a separate system of measurements, the metric system, which now we call SI. So SI stands for French, it's Le Système International. So the SI system of units, we have some fundamental units, and we've got some derived units. The derived units are derived from the fundamental ones. So there are 7 fundamental units of mass, length, time, temperature, electric current, amount of substance, and luminous intensity. Here are the names of the units, and here are the abbreviations. So for mass, the name of the unit is kilogram. It's not gram. Right? Bear that in mind. For length, we use the meter. Time is second. Temperature is Kelvin, not degrees Celsius. For electric current, it's amperes. For amount of substance, we use the mole. And then luminous intensity, we use candelas. And so those, again, are our fundamental units. These are standard physical quantities that can't be derived from other units. We can't break down something like time into some other units, some other quantities that are being multiplied or divided or something. And then we have derived units, which are all the other units that we have that can be derived from the 7 fundamental units. So an example of a derived unit is something like volume. Volume is a length times a length times a length. So it's a cube of length. Right? So volume is a derived unit. So in the metric system, we measure volume in liters. The definition of 1 liter is 1 cubic decimeter. So a decimeter is 10 centimeters, or 1/10 of a meter. If we have 10 centimeters this way, and 10 centimeters that way, and 10 centimeters this way, that volume encompassed is defined as 1 liter. That's how we define 1 liter. Another example is speed. Speed is a distance traveled, a length, divided by a time, how long it took to travel that distance. So this is something like meters per second, or kilometers per hour, miles per hour. So in the US, of course, we use miles per hour, mph, as we drive our cars around. That's a derived unit. But we also have prefixes, because sometimes our units are either really, really big or really, really small, or rather the number is very large or very small compared to the base unit that we're talking about. If we want to talk about the mass of a blade of grass, let's say, it's a little ridiculous to talk about it in terms of kilograms. It weighs way, way less than 1 kilogram. And so we want to be able to use some prefixes. So prefixes modify the size of the unit by a factor of 10 to the n, whatever n is. So if we have our base, that means it's prefix of nothing. So if I just say a meter, I mean something 1 meter long. So that means 1 meter. The exponential notation there, the n in this case is 0 because it's the base. If we get larger units, like kilometer, the prefix is kilo, symbol is K, it means 1,000, which is 10 to the 3. So 1 kilometer is 10 to the 3 meters, 1,000 meters. 1 kilogram is 1,000 grams. Again, note that the kilogram is the base unit in SI, but if we want to get from kilograms to grams, we need to divide by this factor of 1,000. So 1 gram is 1,000th of a kilogram. There are larger prefixes in chemistry. We generally don't use them, largely because, well, if we want to get larger than that, then we just use scientific notation. So it looks something like this. But we do use the smaller prefixes fairly often. So As we get smaller, we have deci, which is symbolized with a D, lowercase. Note that all of these are lowercase letters. Many of the prefixes that are larger than kilo have uppercase letters. So a capital M is not a milli, it's a mega. So be careful how you're writing your prefixes. So we have deci, centi, milli, micro, and nano. So note here that micro has a symbol of mu, that's mu. That's a Greek letter, mu. Nano is just an N. So a deci is 1/10. Centi means 1/100th. So cent means 100. So there are 100 pennies in 100 cents in a dollar. So there are 100 centimeters in a meter. Milli is 1,000th, not 1,000,000th, 1,000th. So that's 0.001. Micro is 1,000th of that. So it's 1/1,000,000th of one micrometer, or 1 micron is 1/1,000,000th of a meter. Nano is a billionth. And so we can see here, now we have negative exponents. So 10 to the minus 1 is 0.1. So 1 decimeter is 10 to the minus 1 meters. 1 centimeter is 10 to the minus 2 meters. 1 millimeter is 10 to the minus 3 meters, and so on. Again, there are units that are prefixes that are below nano, but in general chemistry, we don't generally use those. And so these are the prefixes that you should know. All right, so let's look at a few examples. If I say I have 8 kilometers, what I mean is 8, that's the number, times, now I'm splitting up kilo and meter. Kilo means 1,000, meter means meter. So I have 8 times 1,000 meters. So, or I could also write that as 8 times 10 to the 3 meters. So that's 8,000 meters. On the other hand, if I get a very small unit, like 3 nanometers, it's 3 times the prefix, 0.000000001. I think I had the zeros in there. Should be 8 zeros and then 1 meters. I could also write that as 3 times 10 to the minus 9 meters. And so that's 0.000000003 meters. Again, there should be 8 zeros plus the 3. Right. I want to make a distinction here between mass and weight. Mass and weight are not the same quantity. They're not the same sort of measurement. They're similar, but they're not the same. So mass is a measure of the resistance of an object to change its velocity. Now, generally on Earth, we measure mass using weight because we know the acceleration due to gravity on Earth's surface. So mass is measured in kilograms. But an object's mass doesn't change if I move it from here up into space. It still has the same resistance. It still has the same inertia. Inertia comes from the mass, not from the weight of an object. So the weight is the force exerted on an object by gravity. This is measured in newtons, or in the imperial system in pound force. So note that a newton is a kilogram times meter divided by second squared. So that means that a newton is a derived unit. Right? We've derived it from our definition of a kilogram, a meter, and a second. So the weight of an object changes based on where in the universe it is. If it's here on the surface of Earth, it's got some weight. If it's on the surface of the moon, it's got a different weight. If it's in between, floating in space, it has a third weight. So the weight of an object depends on the force exerted on it by gravity, which changes based on where in the universe it is. But the mass of the object doesn't change. So if I measure the mass of some object here on Earth's surface, if I measure the mass of that same object on the moon's surface, if I measure the mass of that same object in space somewhere, the mass is going to be the same in all 3 places. The weight is going to vary drastically. So you need to be very careful whether you're actually measuring something like mass or whether you're really measuring weight. So most of the time in laboratories, we usually use the weight to determine the mass. Because we know the force exerted on an object due to gravity at Earth's surface, we can figure out what the mass should be. We know that we're measuring our weight in newtons, so kilogram times meters per second squared. We know that the acceleration due to gravity on Earth's surface is 9.8 meters per second squared. So we know the meters per second squared part. So if we measure the whole thing, well, we can figure out what the kilogram part is, what the mass part is. And that's what we're really doing. And so what we have to do with any balance in the laboratory is we have to standardize it, we have to calibrate it using some known mass. So we measure the weight of that known mass in that location. And because we know the mass, now we can figure out, we can calibrate the balance to give us accurate masses with other weights. And so that's really what we're doing in the lab. We're not really measuring the mass. So that was units of measurement.